welcome in. So electromagnetic induction. When you studied the movement of current through wires, and in particular, if you take a look at a solenoid, you can put up a link up above there, you notice that when you pass a current through it, so if it's a DC current, you are able to create or induce an actual magnetic field that resembled basically a permanent magnet, where you had a north pole and a south pole, and the magnetic field would be flowing in, and you would be using your right-hand rule in order to figure that out. So now the question arises, well, can we kind of do the opposite? So can we, through having a magnetic field or some kind of a magnet, even a permanent magnet, can we induce, so without any kind of physical touching or anything of that nature, an actual current flowing through a conductor? And the answer is yes, but it may surprise you in the fact that there is something that has to happen to the magnetic field. So meaning that the magnetic field actually has to change. So there has to be a rate of change in order to induce an actual current which is going to flow. So let's take a look at how this kind of came about, because it was primarily through Faraday. Okay, so this is centuries back, who has experimented and tried to figure out from knowing that, oh, okay, well, if we have currents which are going to be passing through, and we can kind of create these magnetic fields that you saw. So, you use it in the motor principle, for example, use it in solenoids and so on. Then, can we do the opposite? Because it would be great in order to create electricity. So meaning the flow of electrons just through knowing the magnetic fields that you have. So electromagnetic induction is all about this. So, and it does come from the viewpoint of Faraday, kind of way back. And what it does is, or what it allows us to do, is to create an electric current in a conductor with a changing magnetic field. So the key word here is changing. Now, the magnetic field has to change. If it's just stationary that you have and there is no change, so if you put a magnet, again, it's just lying there, there isn't any change, and you have an actual conductor beside it, so some kind of a wire maybe, you'll notice that nothing really happens. But if you take that magnet and start moving it around, you will notice that, oh, this is strange. There is actually current which is induced into that actual wire. So this ultimate item with regards to this induction has been summarized in this particular law. So it is a law of electromagnetic induction within here. And please note, so I am utilizing, so I'll try to point out the sources and also put them up in the description, just so that you can see where this is kind of coming from, and if you want to be able to investigate it further. So this law of electromagnetic induction states, if you have a change in the magnetic field, so it is actually changing, then it will induce a voltage in the conductor. So voltage, remember, is just the electric potential difference. And if you do have that voltage which is induced, then it will automatically induce your actual electric current in a conductor. So that's what the law of electromagnetic induction states. So this is very qualitative, so we're not interested here in the quantitative item. You will learn that a little bit later on. So within here, I just want you to understand that if you have a magnetic field and it is changing, you're going to get, and produce an electric current through it, So let's take a look at some of the other components. Now, I've mentioned the word induced or induction, several times. So induction, technically, if you wanted to be able to think about it, you can think of it as something that causes, or creates a cause or a change, but without any physical contact. So when we say a magnetic field which is changing, and it is inducing a current, there is no actual physical contact in there, but it will have induced. So there will be some kind of a cause or a reaction, where it'll be like, oh, so well, this moving magnet, is creating a magnetic field which is now changing, and it is creating an actual current flowing through the conductor. So that process is called induced or induction that we have. So now the key item is, it's pretty simple. You move a magnet, right? it will create a changing magnetic field, and therefore it will create electricity for us. And so that concept, okay, of moving a magnet, now that particular magnet, okay, which is changing out, it doesn't have to be literally moving, it's the magnetic field that has to move. But if you have a permanent magnet and you start moving it, then you are actually changing the magnetic field, because remember that the closer you are to the permanent magnet, the strength of the magnetic field is there. So if you have a wire and you have a magnet which is right here, okay, so if you're now going to move this, so as you get closer to the wire, the magnetic field is increased, okay, and as you move away, the magnetic field is decreased. So this increase and decrease, so as you're kind of moving a magnet back and forth, okay, it doesn't matter up, down, all around, the magnetic field around it, okay, what the wire experiences is a changing magnetic field that it has. So now, if you wanted to, by any chance, to try to increase the induced current in your actual conductor, you can do it several ways. Now, as you know, you can certainly coil things up, right? So as you coil the actual components of a conductor, so like a wire, and you're coiling it up, you've noticed that as you're coiling it through, you can increase, okay, the magnetic field, but you can increase the current itself as well. So if you're increasing the number of turns or the number of coils, okay, so these turns that you have, you can increase the actual current, okay, which is going to flow. You can also increase it by increasing the rate of change. So, so the faster you move a magnet, or the faster a magnetic field, okay, is moving, then it also will induce a current, okay, which is going to have a bigger strength. Now, the last component, which is the increase, you can also increase the strength of the magnetic field itself, right? So you can take a bigger permanent magnet and bigger, okay, permanent magnet. Now, it's not just permanent magnets and the moving of permanent magnets that is creating this current, okay, in a conductor. You can, please remember that when you have and you pass in like a solenoid, right, where you have a solenoid within, a solenoid can act like a permanent magnet. So for example, what Faraday has done, so this is kind of Faraday's ring, okay, so I'm just taking what he has done within it, and it's been documented, okay, so throughout, you can do something like this, so you can do this test. Now, within here, what you see, so you have, let's say, a battery. So now this battery is going to be DC, right? So for the moment, because that is kind of what my assumption is, that's what you've studied to this point, which is just direct current, so it's not really changing current. So if you have a battery and it creates a current and it starts to flow within here, so you know that now that's, okay, as this kind of goes in, okay, loops around, okay, so it's going to be creating, so this flow, okay, and then it returns back in. So if you took your right hand, okay, you will notice that this actual, okay, path of the current, okay, as it's going through in this direction, would have been creating an actual north pole, okay, on this side, okay, and it would have been creating a south pole on this side. Now, because this is an iron ring, so that actual magnetic field kind of passes along through here, right? So this is your iron ring within here. So it helps along, okay, to pass in, and again, it induces this kind of magnetic field around as long as this thing is on. Now, if you turn it on, so notice what will happen is you're going to create a magnetic field, okay, around here. And of course, you're going to also create a magnetic field all the way around here. Now, okay, as you're passing it along within here, so if you do have, and you start, so if you had a switch within here, so for example, what I'm going to do is, okay, let me just put a switch within here. So I'm going to take this out for the moment. Okay, and we'll put a switch within here so we can close that switch. So when you close the switch, you allow the current to flow. And for an instance of time, even though this might be a DC current, this will induce a magnetic field. And for that little instance, it's going to have a changing magnetic field on this side around as well. And that is what we ultimately would like to do. We would want to be able to induce a current even though there is no physical connection between this side and this side, meaning physical connection in terms of the conductor. So that there is no conductor that is actually, you know, attached within here. So there's no physical conduction within there. What happens is that the induced magnetic field, so within here, caused by the current which starts to flow, okay, will induce a magnetic field around here. And as this is just kind of closed in, then this will create a current in this wire as well. And you can, you know, you can put a galvanometer, okay, right here, okay, so basically an ammeter, so to try to figure out, okay, is there a current which is flowing that you have? And the answer will be yes. Now, because it's DC, so as you close the switch, this will only happen temporarily. So it'll be for a very short, brief period of time. Because when the switch is closed and the current is flowing, okay, the only changes initially when the current starts to flow, there's a changing because it went from no magnetic field to a magnetic field. So there's a change from 0 to some. So during that instant, that temporary instant, you're going to notice that there's going to be a spike in the current, but then it will disappear. Because this magnetic field, although this might be on, sure, there is a magnetic field, but it's not changing anymore. Now, if you had some ability to be able to manipulate your DC, so you're kind of, you know, increasing or decreasing the current, so as you're increasing and decreasing the current, you would have been changing the magnetic field in here, and therefore you would have been noticing that there is a current which is induced on the other side. So that's how Faraday has noticed it. So you would have noticed a little spike on the closing of the switch because there's a changing magnetic field. And you would have noticed that if this was open back up, so it went from a magnetic field to no magnetic field, you will notice that there is a little bit of a change in the current here, and then it goes blank. So ultimately, the electromagnetic induction is about the fact of trying to induce a current in an actual wire that you have, or a conductor of any kind. And you can use this, there's so many different examples that you maybe have heard of. So induction, cooking, okay, that you can do nowadays, okay, where it utilizes this and it uses the electromagnetic induction to create a magnetic field, okay, and then through the resistance, okay, of the actual metal pot that it has, okay, it will start to heat up the pot itself. And it's not like a conduction where it's actually through a physical touch that you have. You have detectors, okay, of metals. You nowadays have induction in terms of charging your batteries on a phone, for instance. So it utilizes this type of technology throughout. And what you should take out of the video is that if you have a changing magnetic field, then it will induce, okay, a voltage in a conductor, and that will induce a current or an electric current to flow. So that is the key, okay, thing that you want to be able to take out. All right, thanks for watching. See you in future videos. Bye, everybody.